Learning causal structure distributions for robust planning. In this work, we find that learning the structural causal model of a robot's dynamics by considering a distribution over causal structures, instead of a single causal structure, gives downstream planners improved robustness. Our key finding is supported by 3 methodological contributions. First, we introduce a mathematical model for the causal structure distribution of a robot's dynamics. Second, we present an estimation method based on feature attribution for the parameters of the causal structure distribution. Here, we leverage the fact that the robot's dynamics only flow forward in time to constrain the search space. Third, we introduce CADI. CADI is a causally informed dynamics model based on a probabilistic encoder-multidecoder architecture that uses the learned distribution of causal structures to inform its latent space. This architecture requires lower computational resources, which is important for real-time planning using the limited computational capacity on board the robot. We have validated the learned causally informed dynamics, CADI, with manipulators and mobile robots in simulation and the real world. CADI supports real-time planning in the real world in structured and unstructured environments. Thanks to its leaner architecture, the dynamics model can be used by sampling-based planners like MPPI to successfully generate control actions for the ground robot. Planning with CADI improves robustness to noise. In simulation, we can see that dynamics learning with causally informed methods like CMI, as well as with correlation-based methods like PETS, that do not rely on a distribution over causal structures show a lower success rate in ground robot navigation tasks whenever the planner needs to rely on corrupted inputs. We can see that CADI, even though it was trained in simulation and directly deployed to the real world, attains higher robustness to common scenarios like inaccurate localization due to noisy GPS readings. In this experiment, we add Gaussian noise, with variance 0.1, to the robot state to simulate such scenarios. The task involves going to a target directly in front of the robot, thus we should expect motion over the x-axis and minimum deviation from the y-axis. The plot lets us see the true robot state during the task, specifically, the deviation from the y-axis whenever the robot is using CADI and the baseline. From it, we can clearly see that sampling-based planners that use CADI show greater robustness to this common and challenging scenario. Additionally, we can see that CADI also completes the task in 1/3 of the total time it takes the baseline to do it. Thank you.